back in, I think it was about 2018, I gave a presentation to RENA, and when I was at DST, and I suppose it was effectively the state of shock testing here in Australia, some of the opportunities we had, potential in the future to look at and to possibly introduce. 3 years later, I guess, I'm now looking at those opportunities, and I thank Phil Thompson from Thornton Tomasetti for taking me on. But I guess if I cast my mind back the last few years, when I was at DST and we were working with Directorate of Naval Engineering, we were always a little bit frustrated with the capabilities we had in the shock area here in Australia. And with the Directorate of Naval Engineering, I guess we introduced the shock standard a few years ago now, but often we didn't have much of a chance to utilise that shock standard simply because we were still building overseas designs, and I guess they came with their own shock qualification requirements. Directorate of Naval Engineering, a couple of years ago, they started to look at the capabilities we had here in Australia. They went round looking at each of those capabilities and the various shock machines we had there. One thing that came out of that for me was that I saw, for instance, in the heavyweight space, we didn't have any capabilities. So when we were working with the Hunter class frigate R&D program there, I thought, well, we should look into building a floating shock platform, which we did. That platform is now up at the NAGAMBIE DST facility, and potentially we can look to start bringing that floating shock platform heavyweight shock testing capability on stream in the next few years. So I guess what I'm trying to do in this particular presentation is, I guess, look at where we can go over the next potentially 5 years, especially with the developments in the naval shipbuilding industry, and hopefully potentially set up I guess what I'm calling here a national sovereign shock testing capability here in Australia. So as Jesse mentioned, I'm now working with Thornton Tomasetti. For those of you who don't know anything about Thornton Tomasetti, it's about 1,500 engineers, architects, scientists and other professionals spread around the world in 5 different continents, and they've got 50 offices and doing about 50 projects around the world, and projects in 50 countries around the world. The majority of people working in Thornton Tomasetti work in the structural engineering side of things, the high level in the structural engineering. So as an example, Thornton Tomasetti has engineered I think it's about 7 of the 12 tallest buildings in the world. And in fact, they've engineered the tallest building currently being built in Saudi Arabia, which I believe is about going to be a kilometre high. So when we look at a small section of Thornton Tomasetti, is the Thornton Tomasetti defence side of things. So basically, it's a multidisciplinary firm of consulting engineers and scientists specialising in weapons effects and also extreme loads on structures and also on equipment and systems, whether that be on naval platforms or in other environments such as from air blast. So the people I'm generally working with a lot are Thornton Tomasetti Defence in Scotland. There's 31 staff operating out of Edinburgh, Bristol and the Lime Hillock testing facility. They do a lot of work in the modelling and simulation side of things in terms of extreme events, weapons effects, safety and security. And of course, I've already mentioned the trials and testing, where they do a lot of UMDEX testing for the UK MOD, the JASO medium weight shock testing machine, which I'll be talking more about in this presentation, vibration work, and also full ship and submarine testing. Thornton Tomasetti also has other defence aspects in the US with 30 staff, or more than 30 staff operating out of New York, Washington, New Mexico and Albuquerque. And again, modelling and simulation is one of their I guess, areas of expertise, looking at similar things such as extreme events, weapons effects, and so forth. In Australia, Thornton Tomasetti has a small footprint at the moment. We're potentially looking to expand that over the next couple of years, especially in relation to defence and shock testing. 11 staff operating out of Melbourne and Perth. And again, I guess the capabilities we're developing or bringing here to Australia will be in modelling and simulation, the trials and testing, air blast, general survivability, vulnerability, and also safety and security. Okay, so look, I guess what I'm going to talk about a lot today is the shock testing of equipment and systems. I thought what I'd do just before I launched into that is just to give you a brief overview of underwater explosions and the effects they have on naval platforms. So I guess if you have a mine, or it could be a torpedo or even a bomb that might miss its target and land in the water, when that bomb detonates, the explosive burns very quickly. In fact, it detonates, produces a shock wave. That shock wave gets transferred into water. And if you look at the bottom left picture there of the overhead, that's a typical pressure profile that you'll get from an explosive charge when it detonates in water. And that shock wave, as it moves through the water, if it passes a sensor, that's the type of response you'll get. You'll notice it's characterized by a very rapid rise in pressure, up to very high pressures, depending on how close or how big the explosive charge is, followed by, I guess, what we call the decay of the shock wave as it goes past that sensor, and then eventually tails off around to the hydrostatic pressure of the local environment. It's very hard to see a shock wave in water. However, in the top left picture there, if we were detonating explosive charge next to a naval platform, you can actually see the effects of the shock wave. So that's actually a cavitated zone next to a surface ship. And when that very high pressure compressive shock wave interacts with the water surface, it actually gets reflected as a tensile wave. And because water can't sustain much in the way of tension, you get that cavitation zone around the ship there. And that's what you can see in that top left picture. So it's worthwhile pointing out, with an explosive charge, there's about 50% of the energy in the shock wave, and about 50% of the energy is also in the combustion products. So when those combustion products, or after the explosive detonated, forms I guess a gas bubble underwater, that gas bubble oscillates very quickly. It expands very rapidly. It's very hot inside. It effectively expands past the hydrostatic pressure point in the water, and then the pressure in the surrounding water gets so great that that bubble begins to oscillate and pulsate underwater. And if you've ever seen explosive charge detonate underwater, you'll typically see the plume that comes to the surface. And what you're really seeing there is that gas bubble as it bends to the water surface. And if you look closely in that top right picture there, you can actually see it's black inside that plume. That's actually the combustion products from the explosive detonation. Okay, so if we get an explosive detonation nearby to a naval ship, typically what happens? Well, there's a number of things from that shock wave and also the bubble that can cause damage to a naval platform. So the first of those, for instance, the shockwave loading, this could be in a far field or a close-in situation, depending on how far away the explosive is. But generally that can cause equipment damage and also hull damage. And I guess up in the top right of this presentation, you can see a bearing, the outer race that's failed there, and that might be typical, for instance, of a severe equipment damage for a bearing that could be inside a piece of equipment. As you begin to move that explosive charge closer into a naval platform, that pulsating gas bubble begins to have an effect on the hull of the platform. And in the bottom right picture there, you can see hull damage there, and this was actually from a mine that detonated in the Persian Gulf back in the 1990s. That's from the USS Princeton, where that mine detonated, and that pulsating gas bubble actually caused hull damage to that platform. And it's no coincidence the fact that weapons designers for underwater explosives try and match the pulsating frequency of that gas bubble, often about 2 hertz, with the natural hull girder frequency of a naval platform, which is also about 2 hertz. And that's the whole idea, is to try and break the back of a ship, especially with a mine or even a torpedo. And eventually, when that explosive charge gets so close to the platform, you're still getting shockwave damage, hull whipping damage. You can also get that gas bubble collapsing onto the hull of the platform. And I guess the easiest way of showing that, and I think I showed this video in the last presentation I did a few years ago, and a few of you would have seen this already, but There was video shot of the torpedoing of the ex-HMAS TORRENS back in 1999. That was with a heavyweight Mark 48 torpedo. It was fired by HMAS Collins. It was actually the first firing of a heavyweight torpedo by Collins-class submarine. So TORRENS was basically anchored in position with a noisemaker inside the ship hull. The torpedo found its way to the submarine and then detonated. And it's a really good video for showing each of these three mechanisms. So the shockwave loading, the hull whipping, and also the gas bowl will collapse onto the hull. So I'll play this video now, and I think there is audio. Hopefully you'll be able to hear it. Whoops, hold on. That didn't go well. Let me just try that again. Hopefully play the video. There, if I just take this video back a little bit. So just before the detonation of the explosive, there's the cavitated zone. That's the shock wave moving very rapidly through the water, typically just under 1,500 meters per second. There's the hogging of the back of the TORRENS there as the bubble begins to expand. It sags again as the bubble shrinks, and then that bubble collapses onto the hull of the platform and eventually vents up through the structure. And go to the end of this video there, you know, you'll see the actual back of the ship is broken. It's broken in half, and eventually the ship sank. Now, that's a great video to show in terms of the mechanisms or what happens with explosive charge. However, I always say it's a lousy video to show what actually typically happens to a naval platform when explosive charge goes off nearby. A heavyweight torpedo, about 300 kilos of explosive, are actually designed to sink 10,000-ton cruisers or bigger ships again. HMAS Torrens was only about 2,500 tons, so it was basically using a big mallet to crack open a peanut in that particular case. So it's worthwhile pointing out that torpedoes are less likely to be used, and there's only been 3 firings of a torpedo since World War II. I think the first of those was back in the Pakistan-Indian War back in 1972 in the Falklands. The UK fired a heavyweight torpedo, and back in it's about 2010, 2009, allegedly the North Koreans also fired a torpedo against a South Korean corvette. But in reality, the biggest threats out there are in fact from sea mines. So whether those sea mines are floating, whether they're tethered, whether they're on the seabed waiting to detonate, or they have rising mines these days which can be triggered acoustically or magnetically, and they can rise up towards a platform. By far the biggest threat to naval platforms is from sea mines. They're effectively low cost, extremely effective. They're a stealth sit and wait weapon. And as I mentioned before, you know, they can listen a number of ways, acoustically or magnetically, and they can even count the number of ships that might go over the top and not necessarily detonate for the first ship that comes through. So how do we, or why do we try and shock harden a platform against sea mines or torpedoes? Well, there's not an awful lot you can do with the structure of a platform. Sometimes we design modern warships with some resistance to shock, but generally the platform is designed for its sea loading. From the sea loading side of things, you can do a few things to stop, for instance, cracks running through the hull and things like that, but generally not an awful lot is done these days. There's a little bit done to resist whipping and things like that. However, from the perspective of equipment side of things, there's an awful lot we can do to protect the equipment on board a platform and help it to survive a much higher shock loading level. And most of this presentation I'll be going through concentrates on the survival of equipment, especially from the shockwave side of things. Also, we can do a fair bit to try and ensure personnel on board a platform are also protected as much as possible. And just quickly looking as that shock wave interacts with the hull of the platform, and actually I've got 3 shock regions here, but I've actually displaying 5 here, but typically what you find here, for instance, is if you look down on this diagram here, as the shock wave interacts with a ship hull, region 1 over here, if you look at this velocity versus time block, you see a very short, sharp response, typical, very similar to that response I showed earlier on of the presentation of the pressure wave as it moves through the water. So the response of the platform is very similar to that pressure wave. As you begin to move through the structure and up through the structure, you can see that the pressure wave begins to attenuate a little bit in both the acceleration and we get increased duration of the loading on the platform. Velocity is usually about the same, but again, as you move further up through the structure, it becomes more like a asymmetric sine pulse, and then eventually a full sine wave pulse as you move and measure that shock response up through the structure. Okay, that was a little bit of introduction to, I guess, underwater explosion physics. I guess the main part of this presentation I'd like to go through in particular is my thoughts about developing an Australian sovereign national shock testing and qualification capability. And I guess over the years I was with DST, one of the challenging things we always had to look at was the fact that we've generally built platforms from overseas designs, and each of those overseas designs has come with its own shock standard that we had to generally test against. So for instance, at the moment, we have Collins class submarines that was from a Swedish design. In fact, it has a US combat weapon system on board. We're about to build TAC class submarines designed by the French. In the surface ship space, we've had the Anzac class frigates evolved out of the original MECO 200 design, and that's from the Germans. We've built Hobart class destroyers from a Spanish design, and now we're about to build Hunter class frigates. We evolved out of the UK. So one of the challenging things we've had in Australia here is that we've had quite a mixture of applicable shock standards to test against. When I was working with with Naval Engineering, and when I was working with DST, we tried to bring in the Australian standard, but you know, it's difficult to bring in when you've got these different platforms you're just basically building and then maintaining. And I guess one of the biggest issues we had was effectively the question about what is the shock survivability of our RAM platforms at the moment, and often it was very hard to define and quantify. So effectively, I guess what I'm proposing here is that we try and have a Australian sovereign national shock testing qualification capability. We use our own standard in the future and apply it to all the platforms that we're going to build. And also we do testing against that standard and also modelling and simulation against that standard. So in terms of our development of this national shock testing qualification capability, I guess what we'd really like to do as part of all of this is to raise our current shock testing and qualification capability from what I'm calling these are my definitions, from what I believe would be our tier 1 capability at the moment up to tier 3. And I guess the case in point is, for instance, I would assess that the UK MOD at the moment are at that tier 3 level. So we should aim to try and be at least at that tier 3 level in the future. We try to ensure that naval platforms built within the naval shipbuilding industry maximise their shock survivability within cost and capability constraints. We need to ensure that we continuously train and develop industry in the importance, significance, and the appropriate methods to ensure the maximum naval platform shock survivability. And the most important thing is that when we do all this work, we need to try and feed all this information back into the requirements, the standards, and into Navy doctrine. And that will help us develop improved platform designs. And that's especially applicable, for instance, with the Hunter class frigate, because we expect that Hunter class frigate to evolve, the design of that platform to evolve quite significantly from the first platform that's built through to the 9th platform that's built. And in this presentation, I guess, looking at this national sovereign capability, there's 4 areas in this diagram on the left, I guess I'm going to concentrate on. First of these, equipment and systems shock testing, full-scale ship shock testing, shock standards and requirements, and also the modelling and simulation side of things. Okay, so I guess looking at what I'm defining as our Tier 1 or current shock capability, this is where I think currently Australia is. We have shock testing occurring. However, it's been somewhat haphazard in the past in terms of the techniques and also the items that we've often tested some of these equipment and systems on board, various types of different shock machines. We've often shock tested without consideration for the platform fundamental response frequency or the likely threat scenarios. And I guess if I cast my mind back to the last 10 or 15 years, when we were working with at DST with Naval Engineering, we tried to bring in the Australian shock standard, and we did bring it in. However, it was hard to get people to test against that because it's always the overseas standards that was the requirement for all the platforms we were building. And I should point out that Naval Engineering did do an assessment of the current capabilities we have here in Australia. So that was quite useful in terms of looking at those capabilities. And in fact, when I looked at those capabilities, that's where I decided, well, look, we need to have some heavyweight shock testing capability here in Australia, and I'll be covering that in the next few slides. So from my perspective, what do we need to do to take us from our current Tier 1 level to a Tier 2 level? And this is probably something we should be aiming at over the next 2 years. We need to make sure we've got a range of established and relevant shock testing techniques for industry to utilise. We need to make sure we've got the appropriate shock testing techniques to utilise to achieve the desired levels of survivability. And that's just, for instance, not putting any old bit of equipment on any old shock testing machine, because you could get any result out of that. In fact, you may end up over testing equipment or under testing equipment in those situations. We need to look at a range of expanded set of shock levels for all the Australian platforms, and we need to make sure that they're compared against the various operational threat requirements that operational planners want those naval platforms to go through. And we also need to consider the ability to perform cheaper, environmentally friendly full-scale ship shock testing, and that's something that's likely to happen within the next year or two here in Australia. Okay, I mentioned Tier 3, and I'm thinking this should be our longer term shock capability, and I guess we should have an aim to try and achieve this in 5 years' time. And I look at Tier 3 and would say that that's the capability, for instance, they have back in the UK, where they test all their platforms. So this is where they have a fully integrated capabilities of shock testing, qualification, shock modelling and simulation, and also the standards. They bring all of that together. And I guess for us, one of the big things that we can do in the future is to bring in the modelling and simulation. I'll be talking more about that in the slides coming up. In fact, just quickly dwelling on the modelling and simulation, that's a predominant technique that they use in the UK. And in fact, when they, with the introduction of modelling and simulation, they may not actually do shock testing in the UK unless there's a requirement. So there's such a confidence with the modelling and simulation these days that, and it's been validated and verified over many years, that they have confidence in the UK that they can just use those models to assess the response of the platforms these days. And in fact, with our Tier 3, I think we should be aiming to have Tier 3 ready to go in terms of the Australian shock standards, ready for the attack class submarine, and probably batch 2 of our Hunter class frigates, in about 5 years' time. And I guess the Hunter class frigates, they're still hoping to have the first of those platforms in the water towards the end of this decade, about 2028, 2029. So if we can implement this Tier 3 shock strategy by then I think we'll be doing pretty well. Okay, so when I talk about these 4 areas that I think we need to consider in all of this, the first of these, the equipment and systems shock testing, that's mainly looking at increasing the number of shock testing types of capabilities we have here in Australia. It also takes into account the full-scale ship shock testing. We've done that a little bit in the past. We haven't done it very well in terms of the way we've done it and the results we've had out of it. We've generally put a tick in the box, excuse me, for the platforms we've shock tested, but a lot of that information hasn't been fed back into our standards, or in fact our any modelling and simulation that we haven't really been doing. Again, it's also expanding the shock standards and requirements that we have here in Australia and utilising those a lot more. But as I mentioned before, the most important part of all of this, I believe, is the modelling and simulation capability that can be brought here into Australia and supplement all of these other 3 areas that I've been talking about. And I guess the main point in all of this is to make sure that we've got safe, survivable platforms. And even though I suppose the Royal Australian Navy has been somewhat of a peacetime navy in the last few years, I guess I don't have to remind everybody that there's a fair bit of sabre rattling going on in the South China Sea at the moment. And if we're planning to send our platforms into the South China Sea, we need to make sure we've got safe, survivable platforms from that perspective. Okay, so talking about the first of those 4 areas, heavyweight shock testing. So I mentioned it was probably about 4 or 5 years ago, I guess we'd identified, there was a lack of heavyweight and also to some extent medium weight shock testing here in Australia. So as part of the Hunter class frigate R&D program that DST was working on, we decided to build a floating shock platform here in Australia. We actually obtained the drawings from Canada, which effectively was a copy of the floating shock platform that they have back in the US. So that platform has been built and is now located up at the new DST underwater explosive facility up at NAGAMBIE in central Victoria. It is a copy of the US MILS 901D heavyweight platform, so we could do replica shock testing on that platform for people who wanted to test against MILS 901D. However, unless we had that platform qualified by Naval Sea Systems Command, it would only be a replica test. Who knows, we may, depending on the demand, we may move forward in the future to look at shock qualifying that particular platform by NAVC. I guess the other important thing about having that platform up there is that we don't have to do MILS 901D testing. We can do any range of testing on that platform, whether it be for various international standards or the Australian standards we have here. And it means that rather than just doing a set test like they do with MILS 901D, we put a whole range of instrumentation on that platform and then obtain any result or do any range of shock tests, whether that be, for instance, testing the capacity of that platform. I think it's about 26, 27 tonnes you can put on board that platform, or whether it could be palletised or shock mounted range of systems and equipment you put on that platform. It should be quite a usable and platform from that perspective. And I should point out the UK MOD, Thornton Tomasetti, does all the heavyweight shock testing for the UK MOD back in the UK. And in the middle picture here, that's actually the original floating shock platform that was built back, I believe, in the 1940s during the Second World War. And that platform is still going strong. So Thornton Tomasetti is looking to bring the capability of an experience of having tested for all those years on that floating shock platform here to Australia. And on the right there, the pictures, you can see the Lime Hillock facility back in the UK, but that facility gets utilised basically once a month, and we're hoping that up in NAGAMBIE we can utilise the floating shock platform, hopefully, for something of that same order of magnitude. The actual floating shock platform we have at NAGAMBIE, you can see here in the bottom right, that's the actual platform as it was being painted. It's at the moment, it's a bare platform. It has a roof. However, in order to do shock testing, you need to put deck shock fixtures on that platform. And above that picture, you can see there's an example of the deck shock fixture. So I guess the recommendation is that we look at all the deck shock fixtures we're going to need. For instance, whether that could be for the Hunter class frigate, or the Anzac frigates, Hobart class destroyers, or even the Attack class and also the Collins class submarines. We can develop those fixtures and put them on that platform. And I guess we need to make sure that when we do the testing, that it's consistent application requirements. I should point out, apart from doing explosive testing, with this particular platform, we're also thinking about doing seismic airgun testing on this platform. And that's just the bottom left picture there is just the floating shock platform back in the UK with an explosive test being done against it. But Thornton Tomasetti back in the UK have developed an alternative test to explosive testing. It's a cheaper test to run than explosive test, but they use seismic air guns against that floating shock platform. Okay, just moving on to medium and lightweight shock testing, I guess. From the medium weight perspective, here in Australia, we had a medium weight shock machine. I had that on a picture of that on one of the earliest slides. That was located up at St Mary's in New South Wales. Unfortunately, that machine has long gone. I think it was about 20 years ago that was decommissioned. So basically, but one of the issues I guess I always had when that machine was utilised for testing was that people said, oh, look, if we've got equipment of a certain mass, and it could have been, say, over 300 kilos up to a couple of tonnes, let's just test that equipment on the floating shock platform at St Mary's. And often there was no consideration for where that item of equipment was going to be installed, on what platform it was going to be installed. So effectively it was a one size fits all like they do in the US. In the US, we just shock tested and we put a tick in the box when if that equipment passed the test. So look, I guess there's been very little in the way of medium weight shock testing capability here in Australia. There are various lightweight machines through various test companies through Australia. And I guess we're looking to continue to utilise those testing machines. And as an example, on the top right there's a lightweight shock testing machine. And there's also various shock drop weight towers, as in the bottom left, servo hydraulic machines and all sorts of things. So as part of this national shock testing capability, we want to continue to use all those machines. One of the things we just need to be careful about is that often people, again, have just put equipment on those machines without the consideration of the requirements or how well the response matches up to the naval platform that the equipment might be going on. And I should point out, a lot of these lightweight shock testing machines only generally do half-sine input pulses, whereas often on a naval platform, you'll see a full sine wave or an asymmetric type sine wave pulse. So this is where we need to be careful how we utilise these machines, but and we need to supervise and closely monitor what's being tested on them and how we're testing those machines. So with that in mind, I guess it's worthwhile mentioning that of a new shock testing technology that Thornton Tomasetti have developed back in the UK, and we're looking to bring one of these shock testing machines, medium weight shock testing machines, here to Australia. It's actually called Jazzo. Jazzo is the Mexican god of thunder, if I remember rightly. But basically, Jazzo will allow you to potentially test up to about 5 tonnes in weight and about 6 metres equipment and systems about 6 metres in length. What it does is to utilise seismic air gun technology. So Thornton Tomasetti have a patent on the use of seismic air gun technology for full-scale ship shock testing, and also for the Jazzo machine here doing medium weight testing. But as I said, we're going to bring that capability here to Australia. And one of the advantages with Jazzo is that because it uses that seismic air gun technology, it effectively replicates the response you'll get on a naval platform in terms of the shock load and the release of energy through the structure as the shock load stops, and also the pulsating gas bubble that you might get, that sort of loading on board a naval platform. And just to give you a quick overview of air gun technology for those who don't know about it, the oil and gas industry developed seismic air guns. So basically, they put about 50 of these guns tow them behind a ship for oil and gas exploration. They detonate those guns. Effectively, the guns are just full of compressed air. You fire them electrically through a solenoid, and then they look at the acoustic pulse that's produced by those guns, how it reflects off the seabed, and then you can determine whether there's oil and gas reserves. So Thornton Tomasetti basically took this technology and have adapted it to shock testing of naval platforms and also of equipment. And I'll just play this video, but in this video here, you can see there are 2 seismic air guns. They're about the size of a, for those in Australia, 9 kilo gas barbecue cylinder. They weigh significantly more than that, but basically when you fire these guns, you'll see there is an acoustic pulse you won't be able to see, but you'll see the outflow of air of these guns, and therefore it's like the pulsating gas bubble you get from an explosive charge. So if I just play this, there's the firing of the guns, the two gas bubbles, and you'll notice they coalesce together as they begin to shrink. And effectively, that's the same sort of response you get if an explosive charge was very close to the underside of a naval platform, and that bubble gets attracted to the hull of the platform in that particular situation. So a little bit more about JASO. Effectively, on the top right here, you can see the seismic air gun inside a water container here. Above that water container, you have a float with a platen on board. So when the air gun fires, it forces this float up. That platen on the float then interacts with the shock table, the platen underneath the shock table, and that's how we transmit the shock load from the air gun into the equipment systems that might be sitting up on top of JASO. And basically you can change the duration and also the intensity of the loading by adjusting the pressure inside the air gun. In fact, you can put other gases inside the air gun apart from compressed air to change that response. You can put different materials in between these platens to also change the loading on the impact table. And I've got a little video here. It shows a simulation of JASO firing. So I'll just play this. So here you can see the in this box here in the center is JASO. JASO is on an ISO skid, so we can, a 20-foot ISO skid, so you can put this skid anywhere in Australia, whether it be testing on an explosive range or take the JASO machine to your facility for testing of equipment and systems. So there's the air gun, there's full of water, there's the float, and there's the shock table above it. And on the side here, we have some restrictors there that you can change the restriction of how far the movement of the table. So full of water here, fire the air gun, you see the float move up, impact the table, and then the table comes back down, and you can have a couple of bounces out of that, and that will replicate, for instance, the response that you'll get on board a naval platform. And there's the limit springs and the stops here, which you can change and alter to alter that loading and duration of that loading. Okay, the second area I'd like to talk about is full-scale ship and submarine shock testing with air guns. I mentioned earlier on that Australia's done a number of shock trials in the past, explosive shock trials on some of our naval platforms. So back in 2003, we shock tested HMAS Rankin, the last of the Collins-class submarines. 1999, we also tested our Minehunter Coastal, and earlier than that, we also did some tests on the Minehunter Inshore. All of those tests were explosive tests where we basically took that platform out into blue water. We had a number of support vessels that were required to deploy the explosive charge. Often the platforms were out there, I think in the case of Rankin, for a month and a bit out at sea. You generally do about one explosive firing a week. Lots of logistic costs, but probably the largest cost was associated with the environmental impacts. So we had to have people, spotters on the water and also in the air, making sure the area was clear of mammals and anything else that we didn't want to get in the way of the shock wave that was produced by that explosive charge. So it's quite a costly process for shock testing with explosive charges. Potentially one of the options we have in the future, and it may be the only option because of the environmental impact, is to use seismic air guns to do full-scale ship shock testing of naval platforms. And I guess, you know, full-scale ship shock testing should be considered as the fourth element as part of the shock testing process. We shock test equipment and systems in the laboratory. We then install them on the platform, and a lot of people think we're confident that equipment and systems are going to survive as it is on the platform. in reality, the installation, the way it's installed on the platform means that that equipment that's passed a laboratory test may fail aboard the platform. So full-scale ship shock testing is a very important part of this whole process. So basically with seismic air guns, you don't take that platform out to sea anymore. The platform stays tied up alongside. You bring in the seismic air guns next to the platform. We typically have maybe about 20 air guns against the platform. They're close to the hull of the platform, so it means in terms of environmental impact, you only need to keep about 25, 50 metres surrounding the platform clear of mammals, and then you fire those air guns. And if you have a misfire or, for instance, instrumentation failure, you can just recharge those air guns with compressed air again and fire them again within a number of minutes. So considerable savings from the cost, and also that dramatically reduced environmental impact. And we've just got a little bit of video here, hopefully play. This is a ex-Oberon class submarine in Canada. I don't think it had all the mass, some of the mass, the equipment systems have been removed, but you can see, I'll show you more of this. There's an air gun array underneath this float over here. But if you just watch the structural response of this submarine, it gives you a pretty good idea of how intense the air guns are. Let's just try it again. Oops. Hold on, let me just get back to the technology. Is going to fail me here. Hopefully not. Let's go one slide back. Fingers crossed. Okay, let's just try that again and play the video.
Oh, isn't it? Oh, okay. No, it was in October, so.
So as you can see, quite a severe loading on the hull. In fact, a lot of hull and shock whipping there. So you can I guess adjust the loading with the air guns. You can move the air guns further away to ensure that there's no hull damage to the platform. But most importantly, the air guns replicate the same sort of resonant frequency response you get on that platform as an explosive charge does. So to this point in time, the UK have now mandated using seismic air guns for shock testing any of their new platforms. They also use seismic air guns for doing heavyweight shock testing against their barge. I showed you that shock test that Canadians have done against the Oberon class. They recently did one of their frigates over there in Canada. US Navy has also used air gun testing against some of their platforms. And I guess here in Australia, it's very unlikely that we'll be allowed to do any more explosive charge testing in blue water, simply because of that environmental effect. So I guess if we're looking, really the only alternative is doing full-scale shock testing is to use seismic air guns in the future. And just to show in some of these pictures here in the bottom left, you can see a large float. You'll see the top of that float in the water next to the ship above. But basically, there's 4 air guns suspended underneath this float, and in the top right, you can see the 4 floats with effectively 16 air guns against this platform. So the air guns have been fired against steel-hulled ships, and in this case, that's also an aluminium-hulled ship. You see them being fired against there. Okay, the third area I'd like to highlight, is modelling and simulation. And this is probably one of our biggest opportunities here in Australia. And I guess we need to think seriously about developing that capability in numerical codes in order to accurately assess the capability of our combat platforms. So there's many modelling and simulation codes out there. However, there's only a very small number of those that have been fine-tuned for doing shock loading assessment, or if they, and many of those codes have never been validated against shock loading and also rapid or high loading weapon events. Of course, you need the appropriate people to run those that software in order to get the right answer, i.e. rubbish in or rubbish out. Otherwise, if you haven't got experience, And effectively, numerical modelling will allow you to give a much better assessment of the survivability capability of that platform, because you can only do testing of equipment and systems up to a certain level, especially full ship shock testing. You can't test at full level because there's danger of damaging the platform and also injuring personnel on the platform. But with modelling and simulation, you can validate that against the testing and simulation, the testing and qualification, and then you can scale that right up and run those scenarios at the full design level. And in many cases back in the UK, modelling and simulation has negated the need for shock testing unless there's been a qualification by testing is required. And the pictures on the right here, for instance, are some of the models that have been generated. The shock test above, this was on a bit of hull plating, some hull valves, and this was a test of the electron beam welding of those hull valves against there. But the appropriate model of that has been extensively validated and verified against the range of testing that's been done. And I guess here's a little bit of chance to advertise for Thornton Tomasetti. So Thornton Tomasetti have been working with modelling and simulation for almost 40 years now. They've actually developed their own specialised code called elastoplastic shell analysis, the EPSA code, and also the non-linear fast explicit NL flex code. All of these codes have been validated and verified over about 30 or more years against the testing that Thornton Tomasetti have done over all those years. And now the other part of all of this is that the advantage with modelling and simulation is you can have full platform models of all your current platforms. And that's what's happened back in the UK. So for instance, Thornton Tomasetti looks after all the full platform models for the UK Royal Navy, the Type 26, similar to our Hunter class frigate, the Type 23, the Mine Countermeasures Hunt class, the Sandown class, etc., etc. And these are full detailed structural models, also with a lot of the equipment and systems also modelled on board down to a lot of detail. Apart from surface ships, they've also maintained the submarine platform models that the UK MOD currently have over there for doing all their modelling and simulation of the submarine responses. Okay, so and I guess if we're thinking about this in Australia to get up to that Australian Tier 3 capability, the things we probably should be considering is to try and develop full models over the next 5 years of both our new platforms, the Hunter class and also the attack class submarines, but also considering there's going to be a fair bit of refit going on for the Hobart class destroyers, the Anzac frigates, and especially the Collins class submarines. The advantage with these full ship models is that you can look at various scenarios of how the structure, for instance, of those platforms could be changed, different equipment and systems that might be put in different parts of the platform, and then make an assessment of the overall survivability of that platform in the future. And I should point out, it's not just the elastic response that these simulation models can do, it's also in the plastic deformation and also the fracture and fragmentation, as in the top picture here, which shows I think this was a close-in weapon detonating against a surface ship. But you can see here the fragmentation and also the plastic deformation that's taking place in that particular hull section. The modelling and simulation can also be used for a range of other things, such as for instance, supporting small, medium enterprise equipment suppliers and advising them how that equipment might need to be modified to survive the shock levels on a particular platform before they've manufactured it. Talking with equipment suppliers, weapon systems, bespoke mounting, looking at different types of shock mounting systems. And Thornton Tomasetti, for instance, have developed a new shock testing mounts called pumpkin mounts. The development of I've gone through shock protection systems. It's also, they can be utilised for air blast, fragmentation and warship in harbour safety cases. So, for instance, there's a requirement, I believe these days, if you're visiting an overseas country, you've got your warship there, they want to know potentially what are the effects of that magazine going up and damaging the surrounding infrastructure. So the modelling and simulation is being used for a whole range of efforts there. And it's worthwhile pointing out the bottom picture here, for instance, shows the detail you can go down to. So these are full platform models where you can model any equipment and system and its response, and also the components as part of that equipment and system. Okay, the final thing I'd just quickly like to talk about is the shock standards requirements. And I guess if we want to get up to the Australian Tier 3 capability, we need to make sure that we can compare and assess any of the international shock standards we have with our Australian DEFOS 5000 requirements. And that means we'll also need to continually evolve the standards requirements. And they do this in a similar manner in the UK, where they have the UK MAP requirements. And modelling and simulation is an important part of the evolution of those standards, as is the equipment shock testing. But basically with modelling and simulation, use that as an input to your standards and shock requirements, and continuously evolve those standards over the years. And that's something we haven't done here in Australia. For many years, I think I wrote the standard naval shock standard back in the late 90s, and it's basically sat like that for many years. But we should be looking to evolve that standard in the future, especially utilising modelling and simulation, and also the testing capabilities that we have. And the final slide I've got here, I guess one of the important things that we haven't done much of over the years is to do regular industry and have for academia through training programs. That we should be covering the underwater shock loading theory, shock testing qualification, modelling and simulation, shock standards, and how we apply all of that to Royal Australian Navy platforms. And in fact, another plug for Thornton Tomasetti here, we're looking to potentially bring industry training sessions to Australia here early in 2022. That will be COVID permitting, but we're hoping at this point in time that we'll be able to do that at least early next year. So look, that's the end of the presentation.